Hello everyone. Today I'm happy to present our work, Deep Isometric Learning for Visual Recognition. This is a joint work with Chong, Xiaolong, Yi, and Jitendra. Over the past few years, we have seen a very fast development of ConvNets in visual recognition. Here we show the famous plot of ImageNet classification accuracies. And as we can see, the accuracy is getting better and better, and meanwhile, networks are also growing deeper and deeper. And after several years of network structure development, the pattern of a neural network has converged to the following form: interleaved convolution and activations, and there are also skip connections and normalization layers to help with the optimization. However, for each of these components, they are always proposed from different perspectives and argued by different reasons. For example, just in the field of how to initialize and regularize convolution operators, there are already tons of methods developed. People starting from considering maintain the variance of signals through the networks, until recently, people starting to consider making the convolutional kernels to be orthogonal. And a similar story happens in the activation function development. People propose various of different form of activation functions for different reasons. And this is also true for how to design residual connections. And we have seen a trend of trying to lower the energies in residual branches, but people always do that for different reasons. And given all of these seemingly disjoint previous literatures, we want to ask one question in this project. Does there exist one principle that can unify and explain those previous methods, at least to some extent? And maybe this principle can provide some guidance of future network designs. And in this paper, we argue that the central design principle is the notion of isometry. In the rest of this talk, I'll first introduce isometric learning framework, which is a theoretically motivated design principle. And then we talk about how such principle can enable us to train very deep networks very easily. And finally, we also show how to redesign ResNet-like structures so that no normalization layer is needed. In particular, we can achieve comparable accuracies with ResNet in ImageNet and better transfer learning ability for other visual recognition tasks, such as object detection and instance segmentation. Firstly, let's talk about the definition of isometry. An operator is an isometry if it preserves inner product. In the case of linear operators such as convolution, it is also equivalent to preserve energies or preserve the norm. One simple example is the identity functions, because of course identity function preserve anything. And another example would be multiplying an orthogonal matrix is also an isometry operator. The intuition of why we want an operator to have such property is that if inner product is preserved, the network is stable in the sense that the signals can be backpropagated to the very bottom, because if the inner product is preserved, the whole system have a singular value to be 1. And there are also some excellent previous theoretical works study the benefits of isometry, but they are kind of limited to initialization points or using the sigmoid or tangent edge activations for analysis, and they do not perform a large-scale studies on some vision benchmarks such as ImageNet. And our network, the design principle is very simple. We want to keep the whole network to be close to an isometry. Therefore, we can keep each part to be an isometry. And we start from the very simple vanilla networks that only contains 2 kinds of layers, convolution and activations. And the way we do that is For convolution, we enforce the isometry by making the operator to be so-called orthogonal, both at initialization and during training time. And for the activation, we take a balance between the isometry and the original nonlinearities of the activation functions and use the shifted ReLU variant of the variant in our network. We will talk about these two in detail later, but I think it's better to emphasize here that all of these components are not new and not proposed by us. So here, our contribution is not proposing some novel functions or architectures to improve the network's performance, but we are choosing one of the many reasonable combinations guided by our unified principle to verify our hypothesis, which is what is the central principle for trainabilities of deep networks. And we also provide very detailed discussions about the connections between our works and also the previous works. So let's talk about each part in details. The first part is so-called orthogonal convolutions. And if we think about, we want to make a convolution to be isometry, we need to think both at the initialization point as well as during the training time. At initialization, the key idea here is to initialize the kernel to be an identity function. As we discussed previously, identity functions are naturally isometric functions. And specifically, if we consider a convolutional kernels to be a four-dimensional tensors, and we can initialize this kernel using the following formula. And visually, if we only consider the first output channel where C equals to 0, and all of the convolutional kernels affected these output feature maps will be a three-dimensional array, and we draw it here. And because we want the mapping to be an identity, we are going to only initialize the zeros kernels in this zero dimension in the three-dimensional array, and only initialize the center positions to be 1. So if we consider the convolution operators operated by these kernels, what we're going to get in these feature maps will be just the identity copies of the first channels in the input feature map. And this also holds true for other channels. For example, in these feature maps, we only have these kernels and initialize its center position to be 1, and other kernels will always be 0. Next, we may think about how isometry can be enforced during training time. Actually, here the convolutional case is a little bit convoluted, as it involves some tedious mathematical deduction. So here we are only going to illustrate using the matrix multiplication case. And if you are interested, you are welcome to go to our paper for the complete details. And intuitively, how matrix multiplication can preserve isometry, or equivalently, how matrix can be orthogonal, is by enforcing this condition. The matrix multiplies itself, and we want the results to be as close as to the identity matrix. And interestingly, we found for enforcing the convolution to be orthogonal, the formula is quite similar. So in the convolution case, we are going to first compute the convolution between two kernels, and then we want it to be as close as to the delta functions. And the delta functions is defined to be 1 only in the center of the kernel height and width dimension, and 0 otherwise. So to some extent, it's kind of like a generalized identity functions in the convolutional sense. And here, all of the things are very vague, and so the rigorous definition and the equivalence between the isometry operators and the regularization terms are derived in our papers. And next, we finish talking about the convolution case, and we can talk about how to encourage isometry in the activation layers. But unfortunately, nonlinearities and isometries cannot be achieved at the same time. So there must exist some balance between the isometric properties and the nonlinearities. And here we show some examples of different nonlinear functions. So firstly, this is the most commonly used ReLU functions. ReLU is not isometric, but it gives strong nonlinearities. Another extreme would be the linear functions. Linear function is purely isometric, but there's no nonlinearities, which means the network cannot effectively learn from data. So maybe the easiest way to combine these two is the shifted ReLU function. So shifted ReLU function is just extend the linear part towards the negative axis compared to the ReLU functions. And in practice, we initialize the amounts of shift to be a negative values and make it as a learnable parameters, and thus it can be trained by backpropagation. Okay, next, we show some quantitative experiments to verify the effectiveness of isometric learning. So firstly, we show that the isometry principles enable us to train very deep vanilla networks that is only composed of convolution operators and nonlinear activations. So here we show the ImageNet top 1 classification accuracies. We're starting from the vanilla networks composed of ordinary convolution and original ReLU functions. And on top of it, we can also choose either to add shortcut connections or add batch normalization layers. And what we found is that none of them can be properly trained when the network depths go to very deep, say like more than 50 layers. And in contrast, our network, denoted as Isonet, can still maintain a relatively good accuracy while increasing the depth, even when the depth is going beyond 100 layers. And this verifies the effectiveness of the isometric principles. And our theory or interpretation also have some practical benefits. So basically, there are some previous works showing that in the ResNet-like structures, if the residual branch has relatively low energies, the whole network is close to an isometries. And this is also confirmed by various empirical studies. We listed some of the literature here where they adding a small scalar less than 1 after the summation of ResNet-like structures. And one question here is how we are going to utilize the form of isometry learning to the ResNet, to the residual learning branch, and maybe we can combine the benefits of these two frameworks. And the answer turns out to be extremely simple. So starting from the vanilla Isonet, where we have interleaved orthogonal convolutions and shifted ReLU functions, we are going to directly add in the shortcut connections just as the original ResNet. And one difference is we have a scalar initialized to be 0, and its learnable parameters can be trained by backpropagations. And in this design, in the initialization point, all of the energies in the residual branch will be 0. So therefore, the whole network turns out to be close to an isometry. And the results are surprisingly good. So basically, we note that our combined residual and isometric network, where we denote it as R-Isonet, can achieve comparable performance as original ResNet structures. So we empirically note that since we remove the batch normalization, there would be some overfitting effect, and we choose to use dropout as our regularization terms. And in all kinds of settings, either without regularizations or with regularizations, our RSONet can achieve significantly better results compared to previous methods without normalizations. One of the benefits of removing batch normalization layers is our network can actually have better transfer learning abilities compared to the original ResNet. So here we demonstrate the COCO object detection and instance segmentation performance. So it can be shown that although our Isonet have slightly lower accuracies in ImageNet, but it's actually transfer better compared to the original ResNet. In summary, in this project, we propose isometry as a guiding principle to design deep networks. And such principle can enable us to train a very deep vanilla networks. And it also enables us to resync ResNet structures so that normalization layers is not needed. We also release our code in the following link. Thank you for listening.